In this video, we will look at the concepts in Chapter 3. Chapter 3 will cover what we call stoichiometry, that is the molar and mass relationships in chemical formulas and chemical reactions. We'll go through the definition of the mole. If we look at Chapter 3 material, it's very important. This is likely the most important material that we will cover this semester, and the material that you will use in the future in chemical processes, in chemical laboratories, and even outside of those laboratories. We'll find out that this concept of the mole is the foundation upon which we understand chemical reactions and chemical formulas. We'll start off with the definition of the mole, and we'll look at determination of the formula for unknown compounds. We'll go through balancing chemical equations, and then we'll spend time in this video going over calculations for quantities of reactant and product in chemical reactions. But we'll also have more videos after this covering the mechanics and going through some practice problems. So our starting place is a concept called the mole. And what your textbook has is what we'll call the pre-2018 definition. So previously, the mole was defined as the amount of substance that contains the exact number of entities as there are in atoms in exactly 12 grams of carbon-12. That is the isotope 12 of carbon. Carbon was chosen because it's very stable material, it's low cost, it's very abundant, it's easy to handle, and those are great things for material. So the phrase here, entity, can be atoms, ions, molecules, formula units, electrons, protons. It could be any type of particle. So 1 mole, as it used to be defined, contained approximately 6.022 times 10 to the 23rd entities. That's to 4 significant figures. So this is a really important number. It's sufficiently important that you should simply remember approximately what this is, 6.02 times 10 to the 23rd power. There are some numbers that you should just have committed to memory because it gives you an understanding of the scale and magnitude of things. You should understand approximately how big a meter is, about how big a gram is, what 1 mole is. These are important numbers to understand. So we sometimes call this number Avogadro's number, and then we'll write it as N, actually as N sub A. We'll see on the next slide. Kind of interestingly, there are estimated numbers for the number of stars in the universe, and at least by some recent calculations, the estimated number of stars in the universe is also around 10 to the 23rd power, so kind of a comical little parallel. But we have this number here, and this is our pre-2018 definition. Now, before 2018, the scientific community and the international metrology or international science community had a couple of what we call artifacts upon which we based standards. But in 2018, it was decided that all of the base units, those 7 base units we talked about in last chapter, in chapter 2, should be based on fundamental constants of the universe. And towards that, we have a new definition of the mole. And that's listed here. The mole, and it's symbolized MOL, is the SI unit of amount of substance, and 1 mole is said to contain exactly 6.022140076 times 10 to the 23rd. So obviously everyone after the 6 is 0 because this is an integral value. And it has that many elementary units. So you can look at that number and you can see our new definition. So you should be able to figure out how many significant figures there are in that number, right? You know, what we did back in chapter 1. And as a fun exercise, I know we're not all together, but the first person to send me an email with the correct number of significant figures for the new value of the mole will get a bonus point on their next exam. So this number is a fixed numerical value. It's called Avogadro's constant. It is written as n sub a, expressed in the units of 1 over mole, and that's called the Avogadro number. And the link down below is the IUPAC, that's the International Union of Pure and Applied Chemists, the IUPAC article that describes this. You don't need to memorize that full number to all those significant figures, but you should know the magnitude, because that tells you, that that's a huge number. Like we said, it's at least estimated to be roughly the number of stars in the universe, at least according to current calculations. It's a huge number. So we can look at some common substances. Here's a series of common substances, and it's the rough size for one mole of each of these substances. You've got water and copper and aluminum and other things here. Now let's look back at the periodic table. We had this in chapter 2, but this now hopefully has a little more meaning for us. If we look at the symbol for each element, of course at the top is the atomic number of protons, in the middle is the atomic symbol, and then at the bottom is the atomic mass. And the atomic mass is the isotope averaged value of the mass of that element in 1 mole of atoms of that element. So for beryllium, for example, which is the large symbol right in the middle, Be, below you see 9.012. There are roughly 9 grams of beryllium metal in 1 mole of beryllium atoms. So this leads us to the concept of molar mass. The molar mass of a substance is the mass per mole of its entities. And for the majority of things we come across, elements and simple compounds, these are going to be between 1 and 1,000 grams of material per mole of entities. Now for the monatomic elements, that is elements that exist as individual atoms in their pure state. So that would be, for example, all of the noble gases. The molar mass is the same as the atomic mass in grams per mole. The atomic mass is simply read from the periodic table. So for neon, for example, that's right below helium in the periodic table. The molar mass is listed as 20.18 grams per mole. So there are 20.18 grams of neon in 1 mole of neon atoms. Now for molecular elements and for compounds, we need to have the formula of that substance to determine what we call the molar mass. So an example here is oxygen. The molar mass of oxygen needs to be based on its molecular formula. So we remember from chapter 2, oxygen was one of those diatomic elements, right? So oxygen exists as O2. There are 2 oxygen atoms per molecule in the most stable form of oxygen, element oxygen. And so what we need to do is we need to take twice the molar mass or the atomic mass unit for oxygen to get the molecular weight or the molar mass of the oxygen molecule. So we take 2 times 16, and we can pop up really quickly and see, if you look over here on the second row of the periodic table, we see in group 16, oxygen, its atomic mass is 16 AMU, or 16 grams of oxygen atoms per mole of oxygen atoms. And so in 1 molecule, then we would have 2 times 16, or 32 grams per mole of oxygen molecules. Now we can take a compound, and let's take the compound SO2. That's a covalent compound because it has 2 nonmetals. You would know how to name that. That would be sulfur dioxide. Sulfur dioxide, then, if we want the molar mass, we take 1 times the molar mass of sulfur plus 2 times the molar mass of oxygen. And since we have sulfur having an AMU of 32, oxygen having 16. We take 2 times 16. We can see that this sums up to 64 grams of sulfur dioxide per mole of sulfur dioxide molecules. Now we can take a little more complicated case. Let's take the molecule listed at the top. That's glucose. Glucose is a sugar. It's an important molecule for us. We actually use glucose to drive a lot of our chemical reactions in our body. That's the molecule from which we derive a lot of energy. And if you look at C6H12O6, that tells us there's 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms in each molecule of glucose. So we can calculate the molar mass of that, and we'll see in a moment that's 180.16. We can break this down. There are 6 carbon atoms. There are 6 moles of carbon atoms. And we can multiply that by Avogadro's number. That would actually get us roughly 36 times 10 to the 23rd atoms of carbon in 1 mole of glucose. And there's 72 grams of carbon in 1 mole of glucose. We can do the same thing with hydrogen and with oxygen. Hydrogen, there are 12 atoms of hydrogen in each molecule, 12 moles of hydrogen atoms in each mole of glucose molecules. There are roughly 72 times 10 to the 23rd atoms of hydrogen per mole of glucose. And that's roughly 12 grams of hydrogen. Oxygen, similarly, there's six atoms per molecule, and that's 96 grams. So if we add up 72, 12, and 96, we will get our 180.16 grams per mole. So that helps us to calculate molar masses, and we'll do some examples of this later on. Here is a very key relationship for you to remember, and you're going to use this so much you'll become very comfortable with it. It's a simple relation, but it's very important to remember how it works. And if you get confused, you can also use unit conversions to understand how this works. So we want to interconvert moles and mass and what we would say number of entities or number of atoms or number of molecules. So the mass is equal to the number of moles of a substance times the molar mass, that is the number of grams per mole. So moles times molar mass gives me mass. That's the key relationship to remember. And if you remember that, you can convert to the next equation. Number of moles is equal to mass divided by the formula mass. Now the number of entities, number of atoms or molecules, is equal to the number of moles times Avogadro's number. And so we see how that works. And if you remember that, then you'll get the second equation. You can derive that. The number of moles is the number of entities divided by Avogadro's number. So these are all key relations to remember, and they'll be very important as you go forward. We'll find out that chemical reactions are articulated most efficiently when we write out the number of moles that are involved in the process. But we don't have balances that measure moles, they measure mass. If you remember, or what you'll see in lab is our balances measure in grams. And so we need to be able to convert grams to moles easily, and that comes from this first relationship here. Very critical. So this graphic summarizes what we've learned. So far, if I have the mass of the element, I can use the molar mass to convert it to the amount of substance. How would we do that? Well, we take mass divided by molar mass, gives us the amount in moles of a substance. So that going from top, the beige box, down to the yellow box in the middle, we divide by molar mass. And to go from the yellow box to the green box to get number of atoms or molecules, then we need to multiply by Avogadro's number. And likewise, if we're sitting at the yellow box and we know moles of a substance, if we multiply by the molar mass, then we get the top beige box. That is the mass of the substance that we're working with. Now, if we want to work this out in terms of compounds, we see that we keep the same yellow, beige, and green box, but in the center of the yellow box, for a compound now, the compound, the amount of compound, if I multiply by the molar mass, then I get the top beige box, the mass of the compound. But sometimes we'll want to know the amounts of individual elements within the compound. So if I take the yellow box on the left-hand side, that's the amount of a compound, and if I use my chemical formula, I can convert that into the amount of the elements in each compound, of each element within the compound. So let's take an example. Let's take sulfur dioxide. We looked at that earlier. So let's say that we have 1 mole of sulfur dioxide. That would be the yellow box on the left-hand side. The chemical formula tells us SO2. That means there's 2 moles of oxygen for each mole of compound. Therefore, in the right-hand box, we could say we had 2 moles of oxygen. We'll do calculations with this later to illustrate this process. Now, many times in many fields, they forego the molar concept and simply work on mass percentages. So, for example, when you go buy fertilizer, if you go to Walmart or you go to the big box store, if you go to a hardware store to buy fertilizer, the fertilizer contains nitrogen, potassium, and phosphorus, and these are typically written as mass percents within your substance that you're buying. So let's look at the relations here. The mass percent of an element X within a compound is given by the following equation. You take the number of atoms of X in the formula, multiply by the atomic mass of X, and divide by the molar mass of the compound, and then multiply that by 100. That will give us a mass percent for X within the compound. So you can do this with oxygen and sulfur dioxide. There are 2 atoms of oxygen multiplied by 16 grams per mole, and you can divide this by 64, which is the molar mass of sulfur dioxide, multiply by 100, and you will get out 50%. You can rewrite that as the following equation, moles of X in the formula times the molar mass of X divided by the mass of 1 mole of the compound. The mass fraction can also be used to calculate the mass of that element in any mass of the compound. So once you have that mass percent, you can take your mass of your compound and multiply by the mass of the element divided by the mass of 1 mole of that compound. And so in this case, we're missing the 100. We've got a mass fraction as opposed to the mass percent. So here we have mass percent, and here we have mass fraction. That's the relationship between these two. Next up, we're going to look at what we call empirical versus molecular formulas. And we won't spend a lot of time on this. Empirical formulas are important for laboratory scientists. They are commonly encountered. We'll spend a little bit of time on it. You'll probably have a chance to work a problem or two on this. Maybe on your exam you have a problem. We won't spend a lot of time on it, though. The empirical formula for a compound is what is called the simplest formula for a compound that agrees with the elemental analysis. So it doesn't tell you the true molecular formula necessarily. It simply tells you the lowest whole numbers of moles of each element within a compound. So, for example, hydrogen peroxide, which has hydrogen and oxygen, has an empirical formula of HO. The molecular formula tells you the actual number of atoms of each element in the compound. So for hydrogen peroxide, this is H2O2. So there's 2 hydrogen atoms and 2 oxygen atoms in a molecule of hydrogen peroxide. So you can see the empirical formula is the smallest whole number ratios, and so it would be HO. And the reason we use empirical formulas is because these are what are experimentally determined very commonly. Now, the molecular formula gives you the actual numbers of moles of each element. This is the most important formula, and this is the one you always want to have access. So the molecular formula is a whole number multiple of the empirical formula. And we'll see an example of this in just a moment, but if you take the molar mass and you divide by the empirical formula mass, you'll get some integral value. The way that empirical formulas are determined are by mass. So typically they use an apparatus that looks like the following. In fact, this is not commonly done anymore. The backside of this is typically handled by a gas chromatograph, but what you have is you take your compound, and very often this is done, it's called combustion analysis. It's done for organic compounds. In the little oven in the center, you have your pile of compound, and then you flow a stream of oxygen across this, and the compound burns. When the compound burns, it typically produces carbon dioxide, water, nitrogen oxides, and sulfur oxides. And so the first end will attach the water. The second one will attach the carbon dioxide, and then further down you can attach other things, but typically, like I say, this is now measured with a gas chromatograph where you can see a peak for the hydrogen oxides or water. Typical for you see a peak for the carbon oxides or carbon dioxide, you'll see a peak for nitrogen oxides, sulfur oxides, and so forth. And you weigh the amount of water or CO2 or other substance produced. You take those weights and you convert them back into molar amounts, and that gives you your empirical formula. So let's look and see a series of compounds that all have the same identical empirical formula, that is CH2O. So CH2O would correspond to a molar mass for that empirical formula of 30 grams per mole. And by mass percent, it's 40% carbon, 6.7% hydrogen, and slightly over 53% oxygen. And here's a series of compounds that all have different molecular formulas. They're different compounds with vastly different properties, but they all have the same empirical formula, CH2O. Formaldehyde has a molecular formula of CH2O as well. Its whole number multiple of them will be 1, and you may have seen formaldehyde before. The second one is acetic acid, which is what gives vinegar its bite, and that it has a formula of C2H4O2. Its whole number multiple is 2. Lactic acid, erythrose, ribose, and glucose, increasing in molar mass across each one of those compounds. As an interesting aside, if someone were to look at all the biomass on Earth, they would give it an approximate empirical formula of CH2O, because most wood, paper, biomass is approximately, the primary component is a glucose unit. Underneath on the bottom of this slide, you see a series of stick figures, and these stick figures are representations, molecular representations for each of these compounds. We'll look at these in more detail later on in subsequent chapters. Now, if we know the molecular formula, we of course know the empirical formula, but that doesn't tell us everything about a compound. We have what we call structural isomers or constitutional isomers. That is, you can have two compounds with identical molecular formulas, but the atoms can be attached in different ways, resulting in different compounds with very different properties. And here are a couple of pairs of structural or constitutional isomers. The first one is C4H10. And hopefully that reminds you of last chapter when we talked about alkanes, the hydrocarbons. And C4H10 in the last chapter for the linear alkanes was butane. So butane is shown here with its molar mass, its boiling point, density, and structural formula. Next to it is 2-methylpropane, which is also C4H10. So that will have the exact same molar mass, 58.12 grams per mole. But it's a different compound. It has a different shape and a different structure, so it has a different boiling point, slightly different density, slightly different chemical reactivity. A more dramatic example can be seen on the right-hand side, C2H6O as the molecular formula, and there are a couple of compounds here, ethanol and dimethyl ether, that are shown, which are structural or constitutional isomers of C2H6O. They both have identical molar masses, 46.07 grams per mole, but you can see the boiling points are vastly different, and the density at room temperature then is correspondingly different because dimethyl ether is a gas and ethanol is a liquid. So you can see that ethanol has orders of magnitude higher density at room temperature. And you can see on the bottom, you can see the structures, the structural formulas for each of these compounds, and then a space-filling picture of what the compounds look like. Next, we're going to talk about chemical equations. Chemical equations are ways for us to express the relationships between compounds in a chemical reaction. Most importantly, the relationships that we write out are molar relationships because we know now, and this has been verified by literally millions of experiments, and that's probably even an underestimate of the number of experiments that have been carried out to verify these sort of relationships. We see that in chemical reactions, it is moles that dictate the amounts of products that are generated in a reaction and the amounts of materials that are consumed. So here's a simple starting example. We can take hydrogen gas and we can take fluorine gas. Those are two elements. We discussed those in chapter 2. They're both diatomic elements. Turns out fluorine is the most reactive element on Earth. It's likely the most reactive element, at least in the known, for us in the known universe. It's a violently reactive element, and it oxidizes, as we'll see later on, it oxidizes every other species. And hydrogen and fluorine react, in this case, producing 2 moles of hydrogen fluoride. HF is a covalent compound, and we can see we would call that hydrogen fluoride as a gas, or if it was to get into water, we would call it hydrofluoric acid, which has many interesting properties, but we don't have time to go over those right now. So we can see we take 1 mole of hydrogen gas and 1 mole of fluorine gas will give us 2 moles of hydrogen fluoride gas. Or we can say 1 molecule of hydrogen gas and 1 molecule of fluorine gas gives us 2 molecules of hydrogen fluoride. On a mass basis, 1 molecule of hydrogen weighs 2 grams. 1 molecule of fluorine weighs 38 grams. So we'll need, even though we have 1 molecule each of hydrogen and fluorine, we only need 2 grams of hydrogen for every 38 grams of fluorine, and that will give us 40 grams of hydrogen fluoride. And you can see this agrees with the conservation of matter. 2 plus 38 gives you 40. And in general, this is the way we write out chemical equations. On the left, we write the reactants. We write an arrow, and that points to the products on the right. That arrow is sometimes called a yield arrow. this reactants yield these products. And the arrow sometimes will have things above or below it. It might be a delta symbol if we need heat to drive a reaction, or if there's a catalyst that's necessary to facilitate a reaction. But this is how we express a chemical equation. One of the most important things is an equation must be balanced. We know from the conservation of mass that the number of atoms on the reactant side must be identical to the number of atoms on the product side. We will do some chemical balancing problems later. Here's a general summary of how we write out chemical equations. We take the statement of what's going on, we write down the chemical symbols. We put coefficients in front of each chemical symbol to indicate the amount of substance, making sure that the amount of substance on the reactant side is the same as the amount of substance on the product side. Finally, we will want to generally write down the states of matter under the given conditions. So this is why it's useful to remember the states of the elements, what phase they exist in at room temperature. So magnesium is a metal, it's a solid, reacts with oxygen, which is a gas at room temperature, to give magnesium oxide, which is an ionic compound, and therefore a solid at room temperature. Now, stoichiometric calculations use these balanced chemical equations to determine masses of substances needed in a chemical reaction to produce a given mass of product in a reaction. The coefficients in the balanced chemical equation represent the molar amounts, or the number of atoms or molecules that are involved, and it gives you those molar relationships that are key. When we're doing an experiment in lab, we need to have this as a mass. So we need to convert moles into grams. We need to know that relationship, and that's where that relationship of grams per mole that we discussed earlier comes into play. So this graphic here is a very useful graphic to think about everything that we've learned thus far. On the left-hand side, we've got in the middle the yellow, which is the amount of a reactant substance A, and we have a yield arrow in the middle leading to an amount of substance B. So the yellow boxes would indicate to us the balanced chemical equation that is going on. We can relate this to the mass of substance through our formula masses to get the beige box in the upper left-hand corner and the beige box in the upper right-hand corner, which are the experimental observables, the mass of substance A that we react to yield a given mass of substance B. And of course, on the bottom, we can think about this at a molecular scale. We can think about the number of atoms of A and the number of atoms that are of B that are involved in the process. You should understand this graphic and how to work with it and how to interchange all of these relationships in this figure. These are all very important concepts. We will do some practice problems in a little bit. Now, sometimes reactions will occur in sequence. So, for example, sulfur dioxide can oxidize to sulfur trioxide, which can react with water to produce sulfuric acid. That's called a sequential reaction, or a two-step reaction. And you'll see when you get to organic chemistry, if you take organic chemistry, sometimes you'll have 5 or 10 or even 20-step reactions. Organic chemists like reactions and making complicated molecules. So then the product of the first reaction becomes a reactant in the second reaction. And you can write an overall reaction by adding the two reactions together and combining them to have a starting product and a final, or a starting reactant giving us a final product. Now we get on to a more challenging concept for a lot of students. Some of you may find this very easy, but this can be one of the most difficult parts of this chapter. So this will require more effort as you think about these sorts of processes. Up to this point, we've written out chemical reactions and we know the mass relationships. But very often when you do a reaction, you don't have stoichiometric relationship between the reactants. This might happen in a case where you're using one very expensive compound reacting with something that's very cheap. Well, you want to make sure that you use up all of your expensive compound, and so sometimes that's called the limiting reagent. That's the compound that gets used up completely, and then you throw in some excess of the cheaper material to make sure that the limiting reagent is completely consumed. There are other cases which, by virtue of their environment, have a limiting reagent or an excess reagent. So there are other cases, it's not just economic. So the limiting reagent is the compound that will limit the amount of product that you can generate in your reaction. The other material then is, the other reactant is called the excess reagent. And knowing how those tie together is determined by the balanced chemical equation or the stoichiometry. And we'll see how to do that later on. Now the next thing is reactions often don't go to completion or they have side reactions. There can be other reactions or processes going on that aren't all expressed in the chemical equation that we have. So the theoretical yield is what we've looked at so far. If I have 1 mole of magnesium with 1 mole of O2, I would expect to get 1 mole of magnesium oxide. In this case, magnesium would be the limiting reagent because O2 I'd have more than I needed. That's the theoretical yield, but for some reason I may not get the full yield. The actual yield is the amount of product that you really get when you do a reaction. And so the percent yield tells you how successful you were in a chemical reaction. It tells you the actual yield of your product divided by the theoretical yield, divided by that amount that you would expect to get from your chemical equation, multiplied by 100. And we'll do some practice problems of this in our next video. So we can see this shown visually here. This is the effect of a side product. So if I have some reactants that go on to yield a product, I can have a side product that drains off or kind of siphons off part of my reactant. So I don't get as much product as I might expect to get based on my reaction stoichiometry. Okay, in summary, here is the thing, a list of the things that you really need to get out of Chapter 3. These are going to be the calculations, the mechanics that we're going to work through in our next video. We need to know the moles to mass to atoms conversion, that figure we saw earlier. You need to know chemical formula to moles conversions, how to do that calculation. You need to know empirical formula calculations. You need to know how to do mass fraction or mass percent calculations. Those are related by that factor of 100. We need to know how to balance chemical equations. We need to know how to do theoretical yield calculations, and then based on experiments, percent yield calculations. We need to know how to handle limiting and excess reagents, and finally, solution stoichiometry. With that, we are finished with the concepts for Chapter 3, and we will move on to the mechanics of Chapter 3 and the calculations, which are more challenging.